Hello everyone, I am Pushpendra Gupta. I am going to present my talk on simultaneous observation of anti-damping and inverse spin Hall effect in LSMO platinum bilayer system. So first I would like to thank to the organizer of this conference for giving me opportunity to present my recent research work here. This work has been published in Nanoscale recently, where we have shown that LSMO platinum system can possess the decrease in the Gilbert damping and enhance spin pumping voltage simultaneously. So before going to the talk, I would give a brief introduction of the topic. So in case you have ferromagnetic spins and you apply high frequency magnetic field, then the spin will start processing around the external magnetic field, and then because of the damping, the spin will come to their initial position. So Landau-Lifshitz has given an initial equation to define this phenomena, but that equation was not able to define this phenomena completely because of some obvious reason. So Gilbert has modified this equation. Basically, he has added a damping term. So here alpha is a Gilbert damping constant. So in case of ferromagnetic non-magnetic system where you expect spin pumping, it has been noted that Gilbert damping depends on several parameters which is listed in this equation. So that can be the contribution because of the intrinsic contribution, then proximity effect contribution. So in case you have cobalt platinum system, then platinum will have some proximity effect induced magnetization that can also lead to the enhance in the damping. And in our case, the spin pumping contribution is the most important contribution. So it has been observed that if in your system you have spin pumping, then Gilbert damping enhances. This happens usually, and then the other contribution can be because of the defects and interface roughness, etc. So it is desirable that your ferromagnetic should have low Gilbert damping. That is useful for application point of view. So there are also some such that how you can control the Gilbert damping. And let me explain what is the spin pumping. So spin pumping is a phenomena where spin angular momentum is getting transferred from ferromagnetic layer to non-magnetic layer. And let's move toward the spin Hall effect and inverse spin Hall effect, which is the important study which we have did in our system. So let's consider you have a heavy metal which have very high spin orbit coupling, and you flow charge current on this. Then because of the spin dependent scattering, electron will feel different scattering. So one type of electron will go in one edge, and another type of electron means let's consider the up spin is going to the right side, the left spin will go to the left side. So you will have a spin accumulation in transverse to the electric charge current direction, and as this have equal number of electron accumulated in left to right, then you will not have any potential difference, but you can detect this phenomena using optical method like optical core, by using optical core effect and etc. But that will be the very qualitative measurement. For quantitative measurement, you need to convert this spin current to charge current. So let's consider the second case where you have spin current and you flow the spin current. Then what will happen? Because of the same scattering mechanism, electron will accumulated in one of the edges of the heavy metal. So now you have spin accumulation which are associated with the electron in one edge, and there are less or no accumulation in another edge. So you can have a potential difference which you can measure by using some advanced voltage measurement technique like nanovoltmeter. So this spin current to charge current conversion is known as the inverse spin Hall effect, and the efficiency of this conversion is known as the spin Hall angle, which is defined as Js by Jc. So for spin pumping study, people have explored ferromagnetic non-magnetic bilayer system, where from non-magnetic side people have explored high spin orbit coupling material like heavy metal, antiferromagnets, topological insulator, wire semi-metal, etc. And for ferromagnetic side, people have explored cobalt iron boron, permalloy, and YAG because of their low Gilbert damping. So our choice was to study spin pumping in LSMO platinum system. So because we have chosen LSMO because of its high Curie temperature, and this is a material which possesses high spin polarization, and this is oxide, so it can eliminate the Joule heating effects also. And from heavy metal side, we have chosen platinum as a standard high spin orbit coupling material. However, there are few reports where people have studied LSMO platinum system, but in all previous reports, this LSMO was prepared by using pulse laser deposition system. Oxide-based molecular beam epitaxy can be a very interesting and technique to deposit this type of material, as you can deposit LSMO layer by layer or very epitaxially. As you can see in the right side corner pictures, these are the lead and read images which taken in situ during the deposition. So our approach was to deposit LSMO using pulse laser or using oxide-based molecular beam epitaxy. So these samples were prepared in collaboration with Professor Thomas Bruckel in Germany. So I have listed the sample which we have prepared here. So we have prepared basically a series of 3 samples. One is the single layer LSMO. Two other samples are platinum 3 nanometer and platinum 10 nanometer on base samples. So here I have shown the schematic of FMR setup, ferromagnetic resonance setup in our lab. So here usually we do measurement like we take the CPW and we took our sample on flip chip manner, means upside down. So sample surface touch to the CPW coplanar waveguide, uh, and we use a polymer tape to avoid the shunting effects. So you can see the here in left side in left side bottom cartoon, here I have shown the representation of FMR signal, that you can see the black solid dots, this and in right side you can see that we have shown the angle dependent of inverse spin Hall effect, that is in blue circles. So when it is expected that when you will change the magnetic field direction from 0 to 180 degree, then spin pumping voltage polarization or also changes. So you can see in one side or in positive field it is negative voltage, but in negative field it is showing the positive voltage. So polarity of the voltage has been changed, which indicate that there is a clear spin pumping phenomena is occurring in our sample. We have performed discrete measurement to obtain the saturation magnetization, which will be useful for calculation of other spintronic, useful for other useful spintronic parameters. Then we have performed ferromagnetic resonance to calculate the Gilbert damping. So we have performed FMR in range of 3 to 16 gigahertz in a step of 0.5 gigahertz, and from we have fitted this by using symmetric asymmetric equation, and we have obtained the line width and H resonance for each frequency, and now the frequency versus H resonance is plotted, and that is fitted by using Kittel equation, from where we have obtained the gyromagnetic ratio value. That value has been used to fit line width versus frequency curve, and from there we have obtained the Gilbert damping constant, which is listed in this table. So as you can see that for single layer LSMO we have obtained the Gilbert damping at 0.01, but for bilayer sample this is significantly reduced, that to 0.004 and 0.0037. This is very interesting, that we have observed spin pumping as well as we have observed the decrease in the Gilbert damping constant. So here we puzzled, because this is not usual case, because usually it happens when there is a spin pumping you will have increase in the Gilbert damping, but in our system we obtain the decrease in the Gilbert damping. So to check the reason why this is happening in the system, we have performed a systematic analysis for this. However, due to lack of time, I will not go in the detail, but I will briefly explain why this is happening. So the reason can be because of the anti-damping like torque. So in case, because we know that platinum has spin flip parameter less than 0.1. So because of this, there will be a creation of non-equilibrium charge spin current density at the interface of the platinum, which will create a spin current, and that spin current will give a backflow of spin current in from heavy metal to ferromagnetic. Usually, spin current happens from spin pumping happens from ferromagnetic to non-magnetic, but in that case, there is a possibility that spin backflow is happening from heavy metal to ferromagnet. This spin current can have two components. One is the parallel to the instantaneous magnetization of ferromagnet, and another is a perpendicular to the instantaneous magnetization. The component which is parallel to the instantaneous magnetization is reducing the spin pumping, but the component which is perpendicular to the instantaneous magnetization is giving an additional spin orbit or bit torque onto this instantaneous magnetization vector. So this torque has been effective up to the thickness of 2 times of spin diffusion length. IIT Delhi group has also observed this similar behavior in permalloy beta tantalum system. So this in case of if your non-magnetic thickness is less than the spin diffusion length, then the spin accumulation dominates over the bulk spin orbit coupling of the heavy metal. That will lead to the creation of spin current in near to the interface at heavy metal, and that will reduce the damping. So that can be the reason of anti-damping, like torque, or that can be the reason of decrease in the Gilbert damping in our system. So here I have shown the inverse spin Hall effect measurement. As you know that this black dots are for the ferromagnetic resonance, and these blue circles are the measured voltage simultaneously. We have fitted this measured voltage by using this symmetric and asymmetric equation. So as you can see, that symmetric equation consists of spin pumping and another effects like anomalous Hall effect, anisotropy magnetic resistance, and another. But asymmetric parts have basically contribution due to anomalous Hall effect and other rectification effects. So if in your system the symmetric contribution is dominating, it means you have high spin pumping, your spin pumping is dominating over any other effects. So we have fitted this equation as a whole. You can see this solid red lines, and also symmetric and asymmetric parts separately. So this gray color is the symmetric part, while the purple color is the asymmetric part. So here it is very clear that symmetric part is clearly dominating. So we have very high spin pumping in this system. So to rectify the other effects, we have performed angle dependent inverse spin Hall effect from 0 to 360 degree at a step of 2 degree. Then we have plotted symmetric and asymmetric parts separately, and then from there we have fitted these plots we have fitted by using these equations, and from these equations the obtained different parameters are listed in this table. You can clearly see that spin pumping voltage is 20.05 microvolt for sample where we have platinum 3 nanometer. This is very high spin pumping voltage for such type of system. So as you know that we have a decrease in the Gilbert damping and enhanced spin pumping voltage. So these are the two contradictory things, and we have observed these things simultaneously. So this makes our system very interesting and very promising. Further, we have calculated the spin to charge conversion efficiency, and that has to be obtained at 0.033 and 0.014, which are similar to the other previously reported values. So here is the summary of my talk, that we have observed very high spin pumping voltage for sample where we have platinum 3 nanometer. We have observed anti-damping in elastomer platinum system in spite of very enhanced spin pumping voltage. So the low damping and enhanced spin pumping voltage makes this system very promising for future spintronic application. So in the last, I would like to acknowledge my supervisor Dr. Shubhankar Vedanta for giving me opportunity to work me in this interesting topic, and also to my lab members who has constantly supported me throughout the project. And thank you for your attention. Thank you, and now I am open for questions. Thank you.